the antisymmetric part, which would be, let's say a factor, some kind of factor 1/2, times the u dy minus is the rotation vector, is the rotation tensor. So in the linear Bose-Nash hypothesis in two equation models, we don't have the effect of rotation at all. That's the first thing. But apparently, even more than that, when we developed the equation for the kinetic energy, let's share somehow my sharing. Oh, I see. Okay. Great. Everything is here now. Okay. When we developed the kinetic energy equation, we take the trace of the Reynolds stress, but what we get is a precise equation for the kinetic energy. Then we push a lot of ad hoc assumptions, like the gradient assumption, and in any case, some weird stuff happens in two equation models. The weirdest thing is that we get the Reynolds stresses from the advective part of the equation, of the deterministic equation, and we use it as a part of the dissipation afterwards. So one might say that two equation models are dissipative without even considering discretization or anything like that. Any questions? Someone doesn't follow, or we okay? To go even further than that, the closure problem, of course, we said two equations is considered to be closed. With for incompressible flow, we have the continuity equations, which means that the divergence of the velocity vector is 0. We have three momentum equations. The pressure we get to constant, and then we have a constitutive relationship between the shear and the mean velocity, or what we call the symmetric part of the velocity gradient tensor. And we have two transport equations. One of them could be, I don't know, it could be for L squared over T, K squared over epsilon times some kind of constant. Constant always changes, of course. At least we need the dimensions to be okay. We usually use the kinetic energy, but we don't have to. Yes, but we don't have to. So what you see here is a development of the Reynolds stress equation, which manifests it the ad hocness even in a more pronounced way. It's a simple multiplication of the operator of Navier-Stokes by the perturbative velocity. And we get each term, the unsteady term, the convective term, all the parts of the transport equations. We get a lot more unknowns. We get a lot more. It's still closed, but the more we take higher and higher moments, the more we get more unknowns, and we seem to never get rid of the closure problem. So what happens usually, that's if we're talking about the Reynolds stress equation, that it becomes also many ad hoc assumptions, which have no, I mean, you can base them on some like Patanka did with the upwind, but there is no really there's no real justification to take a 4-point correlation and transform it to something else. This is black magic. And nonetheless, it is found that at least for 2 equations models, they give quite good results. Do you agree? Madeline, do you agree?
Amir, yes. Depending on what problem it is that you are solving.
Yeah, exactly. They give you pretty much good results because all you get is the average velocity and some kind of, perhaps the integral of the pressure, the lift and the drag. So the resolution is not so good, but we can still say we get a lot more than we would have expected with all the restrictions that are supposed to be included, even though we're using complex geometries. I'm talking only about canonic flows even, but even in complex geometries, we get results to a fine resolution, which are pretty good. The problem is that, so we're talking about 2 equation models. The kinetic energy equation, we know how to develop. We also make ad hoc assumptions. And then, let's go back here. Michelle. And then we get we make some ad hoc assumptions, and then we get, the gradient assumption, we get some kind of transport equation. Then we say, usually what we say is that we can we can do the same thing and get the exact dissipation equation if we want to use epsilon as the second parameter. But it's too hard. Then we use some kind of analogy. We simply divide by epsilon over k times some kind of constant, and we get what we get is the Jones-Launder 2 equation k epsilon. That's fine, and it's okay. But then that's what happened in 1972. Then in the 80s, David Wilcox, whose book probably most of you have on your shelf, took a try at an idea Kolmogorov had a long time ago, and took the specific dissipation. First of all, the k epsilon had some problems. The first problems was his behavior against adverse pressure gradient. Second one was he is wall sensitive. You can't integrate seemingly the epsilon equation through the viscous sublayer. And that's kind of a problem, because either you have to decide to lose some of the resolution. You can solve the drag if you're deciding to use wall functions, and you missed the non-slip condition, or you decide to use some kind of what they call the low Reynolds model, which at the time, and we can still call it that way, the Van Driest damping function, a very nonlinear function, which makes the solution a lot stiffer. And it was not so ideal, but we use it, we still use it. I mean, so then David Wilcox took the specific dissipation and proved that it has an elliptic nature, meaning it kind of communicates with the wall. You can integrate it through the viscous sublayer. It didn't have any problems. It still had it's said to have little bit less problems with the adverse pressure gradient, but I'm not sure this is correct. And in the end, it had a different problem near the boundary layer edge. It used to get strange results from the inlet, I mean the omega equation, and therefore the eddy viscosity would get, you wouldn't get the right eddy viscosity. And so the shortcoming of the K omega of Wilson was that the sensitivity to free flow conditions from the inlet. Here I add a little bit about Kolmogorov. Okay. So we're talking 1980. That's like 40 years ago. I mean, that's what we are doing with simulation right now. We can still obviously can't solve large eddy simulation for solid boundaries for a few reasons. First of them, as Pollard said, complete airplane would be able to solve by following Moore's law at about 2070. And 95% of the mesh would be at the wall, and essentially the wall resolution would be kind of like the Kolmogorov scale. And it's not practical. So what we can see is that we are using, and the theory actually for large eddy simulation is is a lot more solid than that of Reynolds average Navier-Stokes. Of course, in Reynolds average Navier-Stokes, we get no turbulent content. We model all the turbulence. In large eddy simulation, we put a low-pass filter, so we get some of the resolved scales, and we model some of the unresolved scales. So there has been some renaissance of large eddy simulation, especially in combustion flow, where you have the action happening away from the wall. But essentially, there is no use for large eddy simulation for everyday engineering problems, perhaps outside the university. What Menta decided to do, that was before he was even in ANSYS, that was while he was in NASA. And it was at 1992. This means 30 years ago. He did two things in the same publications. The publications refers to aerodynamic flows, and I want to stress that it refers to aerodynamic flows, because not all flows are aerodynamic flows. Yet we saw you see students solving very complicated geometries today. Even an electronic system is a very complicated system. Nonetheless, that you cannot get, there are so many restrictions to two-equation models. Like if you take a square duct, you would expect to get some kind of recirculation at the corners, right? Right? It's not. Yes, but you will not get them with two-equation models because the shear stress penetrates too hard to the corners. You would simply get regular flow. You'd need nonlinear Bose-Nash hypothesis to get. You need something to represent the rotation then, or diminish some of the stress that penetrates some of the stress that penetrates the corners. So after all these let's say inquiries I raised, what Mentor did is he outed, maybe I have it here, and if I do, I will show you the, it's supposed to be here. No, never mind. In one paper in 1992, he developed two models for aerodynamic flow. He called it improved aerodynamic flows. 1992, I remind you. One of them was what's called the baseline model. In the baseline model, what he does is solves for an equation for omega. But what he does, he takes the Wilcox k omega near the wall, where it's an elliptic nature allows it to be integrated to the wall, and then blends it, and that's what he does a lot, blends it smoothly, somewhat smoothly, and it happens at the middle of the boundary layer, more or less, with the Jones-Launder K epsilon transformed into the K omega. Perhaps here you can see the elliptic nature of, by the way, of the K omega. So here you see the transformation from K epsilon to K omega. Here you see the, but it's not a problem. You take a substantial derivative. What you get is the Wilcox equation, but you get another cross diffusion term, which usually doesn't do anything, but in the edge of the boundary layer, it has a tremendous effect. It simply diminishes the sensitivity of the omega to the specific dissipation to free streams values from the inlet, and by that solves the problem of the K omega of Wilcox. So that's the BSL. This in the same, it's important to understand. It's still 1994. In the same paper, he got one step further, and what he did is usually what we do is, I'll show you it. What we do is, if you look at two equations, what you usually get is you find a relation which relates the shear to some kind of constant, let's say A1 times the density. And you see here the production of the kinetic energy and its dissipation. Usually it's 1, but in adverse pressure gradient flows, it's above 1. So what happens when it happens, because of the production of kinetic energy, is you see states, and you're going to see one soon, where the epsilon equation, or for the same matter, the BSL equation, simply does not recognize the adverse pressure gradient enough to separate. It may cause an inflection point and separation. And the shear stress can get 20% even higher, meaning the flow stays attached. So what Mentor did is implemented the Brecho assumption. I mean, I really wrote assumption, but it's supposed to be hypothesis, which relates, as easy as it looks, the shear stress to the kinetic energy, and it's the same. It's the same everywhere except in adverse pressure gradient aerodynamic flows cases. But that's what we have to remember. This kind of Brecho hypothesis could be proven very severe for flows which are not aerodynamic. And Mentor tends to say it every time he lectures, but no one seems to pay attention to it too much. So what we're talking about is 1994. Since then, we had we simply had no advancement in two-equation models. What we had is since then by Volker and Mentor, the variation of the local correlation transition model. It's not something new. I mean, the thing is that ANSYS knows how to do a buzz every time something new comes out. They call it usually a new paradigm. But as one who did his master's on transition, and I mean, I damn read everything I needed to read about. I don't know, the specific area I covered was bypass transition, which means no normal modes, and it is so complicated and secondary and Fouquet analysis. And some kind of small changes in the orientation can cause bootstrapping, and nonlinear effect may redistribute it's so complicated that somehow the LCTM concept, which is not Mentor's, I mean, is taking and almost throwing all the kinds of modes of transition, which are still vaguely known. If you go to the Stanford Turbulence Center for Research for Turbulence, then they still investigate the kinds of transition they have, or in KPH, the oblique transition, the kind of transitions that you get from Klebanov modes, except of one kind of transition, which is considered to be model transition, which you can get from the Sommerfeld equations, which is the Toulmin and Schlichting waves that everybody know. Everything is very vague and very susceptible to little changes in the way that waves penetrate the boundary layer. So saying that there was a way to calculate transition, it was the EN method. You would couple the boundary layer equations, which were to a very high resolution, with the Euler equations, and calculate where transition onset is. I mean, that's the best you could do. Suddenly you have a model that can predict transition over, it was GE, so it actually started from bypass transition. It's probably the single most complex mode of transition that we have, of large turbulence intensity, the different ways of penetration to the boundary layer, different ways of non-normal modes, which grows transiently, and non-linear actions that redistribute the energy because they cannot grow the energy. There's an equation called the Reynolds-Orr equation, which says that the growth should be linear. And it's so, what I'm trying to say, it's such a vague idea that it's amazing that it's caught so quietly that someone says I can predict transition, and all the modes of transition, if you look at Mentas, then I'll show you because I have it here. And if you look at, is the Zoom connecting? Can you hear me? Yeah, but it doesn't matter because I'm going to. Why did it happen? I have this lucky day today. The internet doesn't work like in the old days of put my phone to work. So at least I'll talk in the meantime. Okay, so I need to reconnect, I think. And I'm back. Okay, share the screen. And I'd rather show you it again. This is changed. Sorry for the little bit of technicalities here. Okay. So then, well, as I was talking about transition model, I really would like to show you, except I can't find it right now. And can I go turbulence model? Let's see. Okay. Just a second. I'm very sorry. Wasn't supposed to happen. Okay, can you see the screen? This PDF, the yellow PDF. Can you hear me?
We see a screen, but I don't see a PDF. I see your Google Drive.
You see my Google Drive. Of course, you see my Google Drive. I don't choose in Google Drive. Let me share. Share. Now it's okay, right? Now you don't see my Google Drive anymore? No. Okay, great. Okay. So, besides some kind of changes they made to the K epsilon model and many kinds of ways to close the inability to integrate epsilon, we're talking now about ANSYS. And even the curvature correction that the K omega SST has is the Spalart-Shor correction. I mean, there's simply nothing has been done to change anything about. And here the LCTN, you see two modes, Klebanov modes, and the subharmonic modes. It is so intrinsically complicated to get. This is a largely simulation done by Philip Schlatter. I mean, assuming that you can get in one model everything to fall on one curve by two equations, which are actually, there is of course another problem that there are no non-local operations in regular CFD. So they also take and transform from local correlations to non-local, and I mean, except saying that this is a you see something that reminds you of a transition. There is no relation. I wouldn't trust it for besides the picture of the helicopter that Mentas puts in his work. Then the V2F model, which is a complete failure. It's supposed to solve the problem of secondary circulation, but mostly what it does is fail. It's a K epsilon with two additional equations. Beyond eddy viscosity, we have the Reynolds stress model, which is, I know that none of you have used ever, or maybe you did, Madeline. Did you ever use an RSI model?
No, I have not to date.
No, because it's too stiff and it's too hard to converge, and it gives you none other than, I mean, no turbulent content anyway. Still, Reynolds average, not very Stokes. And so there is, ANSYS added the explicit algebraic Reynolds stress model, which is also not a new invention. It's something which is which is around for more than 15 years. Somehow it got now to the list of models, and you can call it somewhat of a non-linear Bose-Nash hypothesis. Beyond eddy viscosity, there is another very actually interesting and quite fun, I think, they use. Menta and Agorov, if anyone of you heard about the scale adaptive simulation, which kind of uses two-point correlation, and the fact that in two different points the shear layer has a different length has a different thickness, so the eddies do not combine. So you get some kind of turbulent content. You get some kind of unsteady feature. But if I'll open now I have great, I do have it here. If I'll open best practice for large eddy simulations, what I would have to see is that I have to take and check higher moments and take the PSD and check it, and not only do checkup of well, I see some nice Q factor lying around. And that's what happened with the scale adaptive simulation. I never heard it used for anything but nice pictures. Okay, then we get to the hybrid simulations. The hybrid simulations are still considered to be, does some of you work with hybrid simulations? I mean, there are two kinds. There are many different ways to put them in various packages. There is fully non-global, locally global, like the backfacing step, or fully like just simple boundary layer. Or there is another way to look at it, and it's by the way they're derived, which is the monolithic and zonal. Okay, by monolithic I mean you use one equation. That's the detached eddy simulation, like the Spalatal morass. The funny thing in large eddy simulation, and I guess most of you know it, is that it's not closed. I mean, in two equation models, it's closed, right? You have enough equations, enough. Here you have to choose the size of the filter. So they are not closed. But again, according to the size of the mesh, it turns between large eddy and Reynolds average Navier-Stokes. That's the depth. By large eddy simulation, it means we put a filter on the low pass filter on the wave number spectrum, and what is beyond some kind of resolution we model by a sub-bit scale model, which is also but there is a lot more. I mean, it's also problematic, very problematic. We still have problem of commutation between filters and derivatives and other kind of problems. But the theory is a lot more developed than the ad hoc theory of runs. And you get turbulent content, which is important, but you also need to validate it very differently. When we talk about hybrid methods, then there's the family of Spalat, which is just by looking at the names, you see that there's some kind of problems. There's a detached eddy simulation. There is a delayed detached eddy simulation. There is a shielded delayed detached eddy simulation, and there's an improved delayed eddy simulation. I mean, something is wrong there, and the wrong thing is that it seemed to have a problem which is called grid-induced separation. depending on the level of refinement that you use, you might get problems which are simply moving from runs to less when it's not supposed to. The other problem it has is called model stress depletion, which happens when mostly it happens because switching from runs to less is very problematic. I mean, you don't have any turbulent content when you switch to larger simulation, so you need to somehow invent it or by some other manner. Detached steady simulation does show some kind of improvement of the scale adaptive simulation, which is absolutely based on nothing except the von Karman length scale. But detached steady simulation is not used, both because of the problem of the grid-induced separation and the problem of the model stress depletion. So we didn't quite have any until now, and including the improved detached steady simulation. Until now, it doesn't matter if it's Spalat Almaras reframing or K omega like in Fluent. We cannot promise ourselves that we are using a model which we can. You will not be able to validate it, at least not by higher moments or PSD or something like that. About large eddy simulation, I really don't want to talk. It's there are problems with large eddy simulation, but they are known. They are the theory is much more solid. There are problems which are, of course, obvious, but when we talk about zoneless, we still find the same problems. When we move from Reynolds average Navier Stokes area to a zone of large eddy simulation, we need some synthetic means maybe to get a turbulent content, and this is a problem. So the past few years in here it's shielded detached steady simulation, which is another improvement, which is supposed to shield the boundary layer from and again no resolution. I mean, it's usable, but it's usually usable. Not you will not be able to a posteriori validate. You know what I mean? Do a validation after with the turbulent content that you get. What you can do with Valley model or perhaps even Smart Gorinski in some cases. Stress blended eddy simulation. That's in 2016. That's another one of these new paradigm. Is just a platform. It's not a model actually. It's a platform which allows you to use any kind of large eddy simulation that you already, let's say, validated in the past and know how to use with Reynolds average Navier-Stokes equation that you want to use, and saying that it's not a model. I mean, if you you still cannot. I mean, you still might find the same problems that you found with detached ladder simulation. Okay. Zoneless is even more problematic. I mean, problems like synthetic turbulence introduced in the interface, the problem of the gray area, which, as far as I know, why is it happening? Which, as far as I know, are not soluble still. Vortex generators, or there are many ways to do that, but there's a difference when you do it in the inlet and let turbulent content evolve. So you start with some synthetic vortex generator, although you don't have to do that, you can tripwire it, but there's a difference when you do that in an inlet and let the turbulence evolve, and when you do that when switching between zones inside the simulation. This could really cause problems. So there was here some kind of an idea to use scale adaptive simulation because it creates some kind of the meaning of using scale adaptive simulation is just like using the vortex generator. It's the same thing. So all these models, actually what we have here is the Jones-Launder model from 72 with a little bit of with the Wilcox model, and that's about it. Nothing else improved in the way we solve Reynolds average Navier-Stokes equations. And those of you who know McDonald's books, really recommend them. Maybe I will have it here. Of course not. Why would I? It would if you read McDonald's book, then you would clearly understand that there's simply no reason for first of all a deterministic equation to get such an statistical nature. Second of all, it kind of works only because this creature here that we have comes from the nonlinear part. It kind of works because we only get the mean velocity in the one's equation. So that's it. And beyond that, we haven't made any improvement to the Reynolds average Navier-Stokes, even though we tried. I mean, Davidson tried with the V2F, and the scale adaptive simulation was also kind of a lame way to improve it. But the other thing which is unacceptable and ununderstood, I find that don't understand is how after all this time with no changes, most people don't know what the equations mean. That's what I found even more weird. Yes. The realizable model has three invariants, which ensure positivity of the stresses. So it's, I guess there is sometimes that, and it's not specifically known as a high Reynolds model. And that's why maybe it's a little bit more, I mean, how would I call it? Recommended? It's recommended like the SST. But you should be but you should be very wary because what counts in the end is your V and V. I mean, and what counts before the V and V is the way you model the boundary layer, because turbulence needs a wall. And if you've done something wrong in these parts, either you checked your eddy viscosity ratio and it's well outside the boundary layer, or from the other side, you did a validation, but the results are horrible. And so there is not a preferred model. Yes, the SST has an improvement over the BSL. The only improvement it has is when the flow is aerodynamic. It tends to be a little bit better against detect the effect of adverse pressure gradient. What we find, I mean, like in a U-turn or something. The RNG is kind of special because it was derived entirely without ad hoc assumptions. It's one of the. It's the only one I didn't write I didn't write some kind of communicative stuff about it, because they really use the language of quantum field theory there. I mean, they call like high wave number the ultraviolet end, and but usually what they say is that it's a little bit better when thermal issues are considered, and it's a little bit better with turbo machinery, but it's bullshit. I mean, really, I'd rather you do the boundary layer, the orthogonal layers fine and good enough, and manage the truncation error as much as you can, than listening to someone telling you to use a wall-sensitive model and not checking the boundary layer at all. So I don't know where comes the biggest mistake, but usually you cannot control the mistake that comes from the Lance turbulence model. So what's the difference? Whichever works better. There are some, I can show you here, there are some cases which were found to be, where is my world? Here it is. Let's look a bit about the gecko. That's the last thing, I mean, that the gecko is like absolutely nothing. I mean, they gave you 5 numbers which you can play with, but they won't take a responsibility on them. and what you get is two sets of numbers. One of them gives you the realizable k epsilon. The other one is the default. It's the SST. I don't know if there is a future in this model, but here you see a case, a specific case where for an computation of an axisymmetric, non-axisymmetric jet flows, the k epsilon realizable model was validated to have better results than the k omega SST. Something like that. No, here it's about changing the calibration constants, because we remember that we calibrate. This is also a weird thing that happens with two equation models. You know how we calibrate them, right? According to the law of the wall, a flat boundary layer. And then you use it for very complex flows, which is, yes, the chat question there. Okay. Goodbye, Madeline.
I have to run off, unfortunately, but thank you. This has been very informative. I've learned a lot, and I hope to join you again for sessions like this in the future.
Thank you very much. Thank you very much.
Okay, have a good night.
Good night. Okay, so we'll continue. So the gecko offers, it's supposed to offer, here you see you can do the play with, like, the k epsilon doesn't recognize here the adverse pressure gradient. The SST model does recognize it. So you can play with these 5 parameters, which are not calibration constants, okay? They are parameters, and get different results. But you're going to have to check it on your own. I mean, you're going to have to make research to get to these kind of results. ANSYS is not going to take responsibility for validations of for any kind of numbering of the 5 parameters. So part of it acts mostly on the inner part of the boundary layer. Part of it acts mostly on the outer part of the boundary layer. And part of it works mostly on free shear flows, like you see here. There's a specific one for CJet. There's a specific one for having a non-linear Boussinesq hypothesis that you can have here. A non-linear stress-strain relationship. Here you saw what I said before. If you just cover this thing here and put the mu, I mean, this is the antisymmetric part of the velocity gradient tensor. So that's the rotation. It doesn't appear in the kinetic energy nor in the Boussinesq hypothesis. So as a consequence, this is what you get when you have a square duct with a k omega SST model. This is a DNS, and this is a nonlinear stress-strain relationship of gecko. Or you can also use then the explicit algebraic Reynolds stress model, because it's a lot less stiffer than the RSM. Okay, so you can use it if you think you have recirculation areas. There is another way to capture recirculation areas, which is the Jones-Launder correction. Do not use that. It usually makes problems everywhere you have stagnation areas. So be very careful using it. C-curve, that's the spalature. That's the exact. That's the exact. When they built the spalatal morass model, they tailored it to be exactly for open flow wings. Okay, so they offered correction for cases for which you have obviously an adverse pressure gradient because it's a wing, and what this C curve uses is this correction. They simply took it and used it, so it's the same one that this palatal morass uses. So what I'm trying to say, this is how a curvature spalature from the palatal morass curvature correction changes the results for a U-turn. Okay, because we don't have a rotation effect in the K and omega equations. Okay, in the Brzezinski hypothesis. So every time you think you have some kind of swirling flow, or every time you think you have some kind of swirling flow, you apply the curvature correction. This is kind of important. But what I'm trying to say in this webinar, here you see the ranges that they gave for the free coefficients. But again, all they give you is two sets which amount to the realizable K omega and K omega SST. So you can't really do a lot about it. So what I'm trying to say is that actually the Jones-Launder model in 1972 was the biggest step towards two equation models. Yes, the Wilcox made it not wall sensitive, but that's just a different choice of parameter. It was an easy thing to detect, and he also admits it in his book. What Manta did was, again, it was ingenious. I mean, to combine to get this cross diffusion term to cancel the sensitivity of omega outside. But again, everything is based on the Jones-Launder model from 1972. We didn't have much changes, and then with Reynolds average Navier-Stokes since then. And what it means is that they seem to perform a lot better than we'd expect. And we think it's that way because what we check is average velocity without turbulent content, or the drag on a wing, which are very low order things to check. So every year when you hear the buzz about the new turbulent model coming out, the Gecko, the this, the that, I have like 20 posts on models which explain the models, but actually we did not come anywhere closer to solve few problems, hard problems. One of them is nothing was done with the Reynolds average Navier-Stokes. in large eddy in hybrid simulations, we are not able to overcome the problem of the gray area at all. Supply turbulent content from runs to less, and the monolithic derivation, the detached eddy kind, simply do not provide the results we want. That are simply not good enough. Even the best of them are not good enough. So hybrids are pretty much left aside right now. No one deals with them anymore. As far as large eddy simulation is concerned, we are having still a lot of problems with it, but we are able to perform problems like combustion of flamelets that are not wall bounded, WM-less results for a flat wing. You saw probably that picture where it's very simple to make a zonal separation. Comes pretty good. They have done a lot of work to overcome the problems that models like Smagorinsky had, to get the right consistency. I mean, consistency means that you have a few criterions that you want to match when you're besides getting the velocity. You want to keep the entropy. I mean, you want so consistency is very important, and the fact that we are partly, there is now a little bit of setback from ILS, implicit large eddy simulation. For those of you who don't know what it means that you, instead of putting an explicit filter, an explicit low pass filter, you just use numerical objects to actually damp the solution to the Kolmogorov scale, to replace the dissipation. There is a lot of problems with that because there is at least interesting. I wish I told you, Raja, to look at it. Parvi's mind shows how two second order discretization can be much more accurate than a fifth order discretization, because we have issues with participation factors of each of the Fourier. If we take let's say the velocity and break it to Taylor or Fourier, we have participation factors, and the odd derivatives are dispersive, which means they put wiggles inside the solutions, and wiggles could be bad. I mean, they are a disturbance, and they could destroy the results. And the even derivatives are connected to the numerical dissipation. So nothing promises you that using an ILS of a high order would give you better results. And it's very hard to control what the filter actually does when you are using numerical objects. So what they are focusing right now is mostly on dynamic models, mostly on dynamic models and mostly on resolving the issue of how to be able to, even if not be able to commute the filter operation with the derivative operation, then at least having done that with some kind of error which you can check and bound, but not hurt consistency. So what it looks like is that explicit filters are going to be the next thing that will prevail for the till then we'll be using Reynolds average and Navier-Stokes. So to conclude, okay, any questions? This is a lot of material. I mean, I don't bet all of you know all of the stuff I said right now. Shall I ask? Yeah, of course. What is ad hoc? I'll show you what is ad hoc exactly. An ad hoc assumption, first of all, let's have a good look at what we want to do and what we actually get. We want that. We want direct numerical simulations, but we are dependent on the Reynolds number. The Reynolds number is reflecting how well momentum is diffused relative to the flow velocity, the cross-stream direction, or the size of the boundary layer. Don't use the inertial forces to viscous forces because it's not true. But there was we have a constraint of 9 Reynolds in. You can say Reynolds cubes, and for high Reynolds it's impossible to do a DNS, especially if the geometry is you need very high order, also very high order, and sometimes even spectral, I mean infinite order of polynomials, and we will not be able to do this for the foreseeable future. You'll read it everywhere in every publication you must write. It shall remain so for the foreseeable future. So we have the Kolmogorov universality, and what we hope is that when we put a filter, we just cut it like that and not change what is resolved. Okay. With the Smagorinsky model, it had this problem. I mean, sometimes you cut it, or there was a time they tried an method called very large eddy simulation. What happened with very large eddy simulation is that you got here like a line going like that and not, doesn't work. Here you see what I've explained about the gradient tensor, the velocity gradient tensor. Part of it is the symmetric part, which is the shear. Part of it is the rotation. In the Wisniewski hypothesis, we have only the shear, and you have the gamma criterion. Usually we either use lambda 2, or we use the Q criterion to watch it gives us a measure of the vorticity in the flow. Okay? There's a nice movie here, but we won't watch it now. Computational resources, impossible. Modeling turbulence. Okay, so what we do is we do ensemble average, right? Everybody knows what ensemble average is. We do this, yes, we did the same experiment many times. Otherwise, we either don't have spatial average or we don't have time-dependent equations. Here you see what an sample average is. You see there is it's even though it's averaged, there is time here. Okay, and we assume something which doesn't exist, is that we have scale separation. We do have a scale separation between the molecular size and continuum. When we say infinitesimal, and then develop the Navier-Stokes equation, it's the infinitesimal is a lot more than we do have a scale separation. Here we don't really have a scale separation. You don't see it anywhere. So it doesn't matter where you put the filter. There seem to be, besides the side of the resolved scales and the size which is called SGS, there is stress which is called the Leonard stress. This is the stress that relates between the SGS and the resolved. And this one is very important to calculate. If we cannot calculate it, and with ILS we cannot calculate it, then we have a problem to realize how much dissipation are we getting. So that's the Rand's derivation, very simple. The only thing you need to see is that we do whatever we do, and then we get something and something here, and this something here is from the nonlinear advective part of the equation, okay? But when we build the final steady state Rand's equations, let's say we use the temporal average, it becomes a dissipative object. So that's fishy in it of itself. I mean, the equations are dissipative. The law of the wall. You all should remember, nothing matters if you use if they propose you to use SST or BSL, or it doesn't matter which kind of model you use. You need to have at least the right resolution to solve your problem. If you want to get drag, you need to have y plus equals 1. You need to calculate the y, with point y or something like that. If you want to have inside the boundary layer 15 layers, you see y plus c equals 30 starts the inertial sublayer, the log layer, but it doesn't end. It depends on the Reynolds number, okay? If the Reynolds number is very large, it could be 2,000, 1,000. If for turbo machinery, sometimes it's around 400. It doesn't mean that we don't have to have the same resolution here. We have to have the same resolution. If we don't have the same resolution, we will get bad results. So you need to pay very good attention. The way to do that is to, I told you every time before, always use the EVM, the eddy viscosity ratio. It gives you the best way to check how how you're covering the boundary layer, and try to be a little bit smooth when you move from the topmost layer to the mesh. Otherwise, you're also going to get some kind of mistake. So we don't have that's the law of the wall. It's average. Eddy viscosity, non-eddy viscosity. There's an explanation of the Buzzinesc hypothesis. The Buzzinesc hypothesis, you must remember that we everything you see here is true for the molecular level. I mean, if you look at this as molecules, it's true. It's holding its momentum, and you cut a Taylor series after I don't know one object, and you get the molecular viscosity to a great degree of accuracy. Okay, you see 2 times the mean free path, but when you use the mixing length theory, which means you take the molecule and call it a parcel, the V-thermic you call a V-mix, and the velocity of a molecule you call a perturbative velocity, then there is no real justification for that, and because of that, it changes. It's a flow feature, not a fluid feature. Okay. Here you see the full derivation. You can have this if you want. And here you see the laws that someone asked me the first time. What do I need to do to ensure that I'm at the right continuum level? Okay, so there is a number called the Knudsen number. Its relation with the mesh and the mean free path should be like you see here. And the same, there is the gradient and the ratio between the terminal velocity and the gradient should be very, 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 very large than the mean free path. If this happens, you can use the analogy of molecule parcel. Mean free path is a mixing length. You do the same exact thing, and here you see the Buzzinesc hypothesis. Okay. Shortcomings, we told you before. Flows with sudden changes in the mean strain rate. Okay, there is no history effect in the Buzzinesc hypothesis. Flow over curved surfaces. We don't use the antisymmetric parts. Flow in ducts. What I told you about the square duct. The shear simply penetrates too hard to the corners, and the same happens when you use these models against adverse pressure gradient. They tend to stick more than they should. Rotating flow and stratified flow, nothing to even think about. 3-dimensional flows, by 3-dimensional flows, I mean like if you have a building and a straight roof, then you have separation, and what happens inside the separation is totally unrealizable with a Run's model, okay? You need to have turbulent content to imagine what happens there. Then zero equation. Okay, you asked me about ad hoc, right? Who asked about ad hoc? Okay. Okay. How do we get the kinetic energy? We simply take the trace of the velocity tensor. Okay? We simply take the trace. And then we get something here which is, you can take I'll send it to all of you the same. You see, this is the exact equation for the ensemble averaged. Actually, it's not the ensemble averaged, it's the time averaged. For the kinetic, but the thing is that eventually we do not want these objects to be here. We don't want any perturbative nothing in the equations. So what we do is ad hoc assumption. We call the first part a pressure walk due to only turbulence. The second part, the triple correlation here, that's a transport of turbulent kinetic energy due to fluctuations. And everybody of them makes some kind of weird sense. So we turn them for these two. We use the most popular thing to do is use the gradient. See, this is an ad hoc simplification. You see, we are left here with no perturbative velocity except the Reynolds stress here, which we can switch for, constitutive law, because it's mu t times. This is the gradient assumption. This is the dissipation. The ad hoc assumptions means that they are ad hoc. I mean, they are not in any way justified. They are not justified even isotropically. It's that bad. But we get good enough results because we are not looking in, when we solve runs, the pictures might be beautiful, but we are only solving for the average velocity and a little bit of forces. So this is ad hoc assumptions. Taking these things here, naming them, and the ad hoc assumption is that I understand what's the phenomenology of this triple correlation, and I can switch it with something which I can later solve as a transport equation. Okay? In the end, you can get the final form. Again, you see that's the gradient assumption. It's very known. Epsilon, that's the production of the kinetic energy. Here, what you do to get the epsilon equation, you simply multiply by epsilon over k over epsilon over k, sorry. And you get the analogous equation. Then you calibrate it according to the flat plate boundary layer, which is also kind of weird. I mean, we solve very complex problems of electronic systems with heat sinks, which are kind of the exact tubes that we've shown that there's no recirculation there, so we are supposed to get a mistake in the pressure drop, but then the mistake is that instead of 5-inch pressure drop, you get a ½ inch less. So it's not that important. That's what I'm trying to say. Okay. Anyone has any questions? So we're going to sum it up. The issue here is that we haven't made any kind of progression in the last 20, even about 30 years as regards to runs. we shouldn't be too enthusiastic about what they tell us in the what the vendors tell us. Creo and Discovery Live is the crappiest crap in the world. It's simply crap, and you should at least understand the bit of things that didn't change for 40 years here. Okay, and if you decide to be able to do that, you can and a little bit of discretizations and remember what this means, and then you'll be a CFD, sustainable CFD practitioner. Okay. Does anyone but want this 93 pages of you'd like to have it? So I'll send you now. Yeah, that's cool. Of course. So let's look for it. Second. You're only 3, right? Each of you can tell me his. Let's check. Turbulence. It appears in the. By the way. It's not me. Easier. Okay. Come on, shoot emails. Okay. So Rajat, you have it? Do you have it? Rajat is supposed to have it. Problem is that okay. Okay, each of you, just tell me your names. We'll do it simpler. Okay, Rajat, I have you here. Wait a second. Rajat, Valia. Message.